person, okay? So go to person here, and in person, under agent, there'll be some code here. And this code, once again, matches the basic criteria we specified earlier. So it's going to compute an on-before step some information based on its own state and the state of those around it. And then it's going to update its state based on that information it had previously collected within the on step at the time of on step. So when it actually comes time to step. So here it's collecting some information, and here it's using that information to determine its state. What aspect of its state is it changing within this final event handler? It's changing its what? We didn't see this in that model we saw earlier, the game of life. We didn't see this type of state update, but it's changing its position. So I want to draw a contrast here. Forgive me for repeating it. Earlier with the game of life, we had these cells that had fixed positions, and each of them had some state which would change over time. An agent could be born in them, live and die in them. But those agents themselves were not captured separate from the cells. Here we have a situation where we have people who happen to live in certain cells and can jump to empty cells, for example. But they move between these cells. And an aspect of their state, an important aspect, is where they live at a given point. So even though they may look similar, they're both on a grid, involve empty cells and non-empty cells, they're quite different in the sense that here we have agents moving between locations, discrete locations. Previously what we had is cells that had a fixed location.
So
yeah.
Since we're in like a discrete
Mhm.
environment,
Yeah.
they're really only, even though even threshold is a percent, they're really only 5 thresholds, right?
Correct. What you're alluding to, I think, is that there's sort of, for all, there's only, functionally distinct is a good way to put it. There's different ranges that yield precisely the same behavior. And within that range, there's not going to be any change because the ranges are defined by what the fraction or percentage, as it were, you can view it interchangeably, of your neighbors that are of your same color. And yeah, exactly. So it's either 0% or 25% or 50% or 75%, or all one. And so whether it's 76% or 77% is immaterial. Yes, that's exactly right, and that's a very perceptive comment. So here, though, what we do have is a calculation on before step. So again, we have this lockstep updating by these agents in this grid. And before anyone updates, they're going to collect information on their neighbors. And what information are they going to collect? Well, they are going to find out who their neighbors are. And when they find out who their neighbors are, the first thing they do is to check if what? What do you think this is checking? If neighbors equals null. Yeah, are there any neighbors? If there's no neighbors at all, it treats the person as satisfied. Okay, so if I'm living with no people around me, I'm treated as good enough. If I do have neighbors, then I'm going to accumulate. You've seen this pattern before. Where did we see this sort of pattern? Where we initialize this count to be 0, and then we incremented this count. What is? Yeah, it's a game of life. And basically, what is this thing doing here? It's looping over my what? My neighbors, and it's counting up the number that what? That have the same color as me. And what is this thing here where it's doing that person? Yeah, it's casting it. It was a type coercion or casting. So it's treating agent A as a person. This is the same pattern we saw before. Before we had to treat it as a what? In the game of life, we treated it as a cell, because that was our agent class there. This is our agent class here called persons. We have to treat as a person. That's the pattern you see, because it doesn't know about color in general for agents, because that color was something we like this. We could have called it color with a U, as we do in Canada, and then we would have said the color. So it doesn't know whether you're Canada or US, and so it's not going to automatically know that it's got a color. It's not smart enough. Okay, so we accumulate that information on satisfied and on n sane, and then we determine, so if you have no neighbors, this handles that case. If you do have neighbors, you count the number that have the same color as you.
What does that mean?